Hello, my name is Eric Clausen, and I'm the author of the topographic map mystery, Geology's Unrecognized Paradigm Problem. And in that book, I illustrate dozens of examples of topographic maps that show drainage system and erosional landform evidence that the accepted geology and glacial history paradigm does not enable geologists to adequately explain. And as a result, geologists have been ignoring this evidence for many decades in the past. This map here that you're seeing shows an area in east central Oklahoma, and it's showing the drainage divide with the dashed red line here between the Canadian River drainage and Red River drainage. Now, the Red River is 150 to 200 kilometers to the south of us here, whereas the Canadian River is practically right next to the drainage divide. So this is an asymmetric drainage divide. Geologists know it's there. It's been mapped in great detail. But geologists do not have a good explanation for why the drainage divide is where it is and how it developed or when it developed. So this is an example of what I will be referring to as anomalous evidence or evidence that the accepted paradigm does not enable geologists to explain. Now, this lecture is the second lecture in a series of 4 lectures. You don't need to have heard the other lectures to understand this lecture, but I am going to review just a few things that were mentioned in the first lecture so that you aren't lost in this lecture. One of the things I introduced in the first lecture is what scientific paradigms are. Scientific paradigms are sets of ideas and that basically define a scientific discipline. So the geology discipline is defined by what geologists have agreed are the key ideas that they can share and they can build on each other's work from. Scientific paradigms are essential if a scientific discipline is going to advance. So I don't want to say in this lecture that scientific paradigms are bad because they're essential, but that scientific paradigms have the characteristic that if you use them and if you look closely, the scientific paradigms also enable scientists in that discipline to identify anomalous evidence or evidence that the paradigm does not explain. And that's what we're going to be talking about in this lecture. We're going to be talking about evidence that the paradigm does not explain rather than evidence that the paradigm explains. And in the previous lecture, I also looked at some problematic accepted paradigm interpretations that make drainage system and erosional landform evidence on the topographic maps very difficult to explain. And that includes the concept of pre-glacial north-oriented drainage systems in the northern half of North America, and the concept of multiple interglacial glacial cycles during the Pleistocene. Now, topographic maps, I also illustrated topographic maps illustrating unexplained Delaware River direction changes, water gaps, and barbed tributaries. Now, the map on this slide shows a lot of anomalous evidence. The map was produced more than 100 years ago, and it's showing an area in Pennsylvania. This is Shamokin, Pennsylvania down here. This is Danville, Pennsylvania here. This is the north branch of the Susquehanna River flowing in a west direction here. It will join the west branch of the Susquehanna River over here, and then the Susquehanna River flows in a south direction to the south of here. Now, the anomalous evidence There's lots of anomalous evidence on this map, but what I'm going to point out is our three water gaps. Shamokin Creek starts here in the Shamokin area. It's a relatively minor drainage system, at least compared to the Susquehanna River, and it has cut a deep water gap across the ridge that you see here, known as Big Mountain. Then it makes a jog as it goes west, and then it turns north, and it's cut another deep water gap across this ridge, which is known as Little Mountain. And then it keeps flowing in a north direction. It's cut another deep water gap across this ridge here, and it continues north before turning in a west direction here to join the Susquehanna River to the west of the map. So the water gaps are examples of anomalous evidence. They've been mapped. This map, as I said, has been in existence for more than 100 years. There are much more recent maps showing the water gaps in much more detail. Geologists have mapped the geology of the area in quite a bit of detail. So they can tell you a lot about the geology of the area, but they cannot tell you the circumstances about when, how, or why the water gaps were eroded. Now, I want to, before we get into the crux of the lecture, explain why I think understanding drainage system and erosional landform features origins is important. I think that drainage system and erosional landform evidence, all of these features almost certainly developed during Cenozoic time, and that's the time period since the dinosaurs became extinct. And any correct interpretation of Cenozoic geology and glacial history should be able to explain most of the drainage system and erosional landform evidence that the detailed topographic maps show. And as I've already said, geologists have been unable to explain most of that evidence. And for that reason, they've been ignoring the evidence for more than 60 years. Now, to go back and see where this problem developed, William Morris Davis, who is sometimes referred to as the father of geomorphology or the father of American geography, and in this lecture, I'm going to refer to him as the father of geology's unrecognized paradigm problem, because he was one of the first to try to interpret the drainage system and erosional landform evidence on new topographic maps as they were being produced by the United States Geological Survey. In fact, he strongly supported getting funding for that mapping project, and he was very interested in trying to use those maps to explain drainage system origins, but then he concluded that the evidence was so mysterious that only advanced students would be able to solve those origins. And as I will point out, in 1889, he published an article called The Rivers and Valleys of Pennsylvania, and as a result became the expert on Pennsylvania drainage system. Now, Davis was a very influential figure in the development of geography and geomorphology, which is the study of landforms and drainage systems. And to understand how Davis had such influence, I think we need to go back and look at his boyhood. And Davis, at least during 10 years of his boyhood, after living in Center City when he was very young, lived at this location here. And there is a historic marker there, but the historic marker does not honor Davis. It honors his maternal grandmother, Lucretia Mott. Now, Lucretia Mott was an ardent 19th century women's right advocate and abolitionist, and she probably passed on many skills to Davis as Davis was growing up about how to influence people and get a point across. And also, because while Davis was growing up, The Davis family lived on one side of Old York Road, while the Mott family lived on the other side, and this location is just outside of the Philadelphia city limits. Now, Davis's father, he had some partners in his business interests, but he was a real estate investor and developer who owned and eventually developed large areas in Cheltenham Township, which is just on the edge of Philadelphia here. He also owned a coal mine and a railroad in Bradford County, Pennsylvania, and he owned thousands of acres of coal lands in Harlan County, uh, Kentucky. So Davis grew up in a fairly wealthy family, and throughout his life, he had plenty of money to travel and to do whatever the things that a fairly wealthy person might want to do, although he didn't inherit all of his father's money. Now, we need to place Davis in the right time frame. Davis lived from 1850 to 1934, which was before anybody knew anything about plate tectonics. But Davis was able to outline major Pennsylvania geologic events in a manner that's not too different from how geologists describe those Pennsylvania geologic events today. He also wrote most of his published papers before radiometric age dating was available. So he could only place geologic events in order, and he had no way to measure absolute time. And as I mentioned, he strongly supported efforts to fund the then new United States Geological Survey topographic mapping program. And he claimed that he studied all the new topographic maps as they were issued, at least for a period in his career as a Harvard professor. Although not the topographic mapping project continued for decades after Davis's death, and many parts of the country were not mapped during his lifetime. Also, the concept of continental glaciation was brand new when Davis was attending school and college. And while he later wrote about alpine glacial erosion and to a lesser extent about continental glaciation, like most geologists of his time, he did not see continental ice sheets or the meltwater from those ice sheets as major erosion agents. Now, you probably have been introduced to some of Davis's interpretations, even though you didn't know that they were his interpretations, because many textbooks that are used in grade schools, middle schools, and high schools, and even college and introductory geography and earth science or geology classes describe erosion cycles where there's a useful stage where a relatively flat area is uplifted and streams begin to cut narrow valleys into the area. The flat area Davis would refer to as a peneplain. And then there would be a mature stage when the stream valleys have widened and the upland areas have shrunk. And finally, there would be an old age stage when the region would be reduced to a peneplain again, or a very low relief surface. Now, these erosion cycles were how Davis wanted to explain how regions eroded. And when he started looking at the topographic maps, he tried to explain the evidence in the context of those erosion cycles. Now, as I said, Davis wrote in 1889 in the then new National Geographic magazine about the origin of Pennsylvania drainage systems. And he started in what the geologists consider the Paleozoic, probably towards the end of the Paleozoic era, with a high mountain range in what is now the coastal plain and the Piedmont areas of southeast Pennsylvania, New Jersey, and Maryland and Delaware. And this high mountain range is recognized still today. The origin of the mountain range in Davis's day was not related to plate tectonics. Today, it's related to the collision of two plates, but that the high mountain range is was here, and Davis sees that based on geologic evidence, it's good evidence, that there was a lot of drainage from that high mountain range in a northwest direction. And Davis named the river system that carried that drainage the ancestral Anthracite River. Um, and then he proceeded from that ancestral Anthracite River that flowed in a northwest direction to show how the Anthracite River was gradually dismembered and reversed to create the drainage systems and features that we see today in Pennsylvania. And his paper was very well received at the time. Today, it probably is considered totally obsolete because Davis didn't have a good concept of absolute time, but that it was a very well received research paper, and Davis made his name basically with that paper. Well, at the same year that he published that paper, Davis also published a very short paper in which he used this then new Doylestown topographic map, and he had actually received an advanced copy of the map because the map has a date of 1890 and Davis's publication is 1889. And in that paper, which is only about 1 page in length, he looks at the Doylestown map, and this is Doylestown here. This is the Delaware River flowing in a south direction here, and this is Tohickon Creek, and this is Deer Run, which is a northeast-oriented Tohickon Creek tributary, and this is the east branch of Perkimon Creek, which is flowing in a southwest direction. And this is the north branch of the Chamonix Creek, which begins right here and is flowing in a southwest direction too. Well, Davis focused on this area here, and he argued that Deer Run has captured some of the Perkimon Creek drainage system here. And he argues this is because there's a much steeper gradient here. And so that Deer Run, he's calling it a river pirate. But what's significant about this is that this map showed all kinds of other features. And in just this area here, Davis says nothing about how the asymmetric divide between the Delaware River and Perkimon Creek developed. Perkimon Creek doesn't flows to the Schuylkill River and is not a Delaware River tributary, except in the fact that the Schuylkill River is a Delaware tributary. And he says nothing about the asymmetric Neshaminy Creek Delaware River divide. He says nothing about the valleys that cross the drainage divide and link these northeast oriented Delaware tributaries with the southwest oriented Neshaminy Creek headwaters. And he says nothing about the fact that this drainage divide here between Neshaminy Creek and Perkimon Creek drainage basins is also the drainage divide between the Schuylkill River drainage basin and the Delaware River drainage basin. These things should have captured his attention, but he's busy trying to explain how this fits in with his erosion cycle, and he's not seeing these other features that he should be seeing. And to further look at how he was missing things, as I said, Davis grew up on the edge of the city of Philadelphia, and this is map that was produced in 1893. It's 4 years after he wrote his Rivers and Valleys of Pennsylvania article. So he didn't have the advantage of this map when he wrote that article. But this is the Philadelphia city line here. The number one points out where Davis lived. Then this is Oak Lane here, for those of you that know Philadelphia's neighborhoods, and where the Davises lived was in what is now Melrose Park. Elkins Park would be about here. This is Jenkintown, and this is Noble. And I'm going to show you this area in more detail in the next slide. Davis got this map, I'm sure when he got it, he must have spent many hours looking at it, puzzling over the features here, because he must have known the features in this area around his home to some degree, and he must have been curious how they formed. Now, looking at the area immediately to the north and east of where Davis lived. This is where he lived. This is Jenkintown here, and this is Noble. And at Noble, there's a valley. It's a dry valley. There's no stream that flows continuously across. There are streams going to the east and also to the southwest from it, but in the middle of the valley at Noble, it's a dry valley. And when you go on Old York Road today, and an Old York Road was there when Davis was there, and I'm sure he got to Jenkintown, and I'm sure as a boy that he must have gotten north of Jenkintown and gone down into the valley at Noble, and then come up out of the valley on Old York Road, which you can do today very easily. And he must have puzzled, how was that valley eroded? Well, we have no clue what he thought about that. And then up here at the number 3, this is now Ardsley. And he must have wondered about how the wind gap here, this is a wind gap cut in a sandstone ridge, and he must have puzzled over that. And then at the number 4, there's also a wind gap. And today, well, in Davis's day, and also today, the railroad goes through it, and also Limekiln Pike goes through it. And Limekiln Pike was there when Davis was there, so he must have traveled through this at least on some rare occasions. And so, and I suspect he even noted this on the map, because somebody on the 1893 edition of the map, I'm showing you the 1894 edition. On the 1893, this wind gap was not shown correctly, and somebody raised a big fuss, which caused the United States Geological Survey to reprint the map showing this wind gap correctly. And I don't know who raised the fuss, but it could very well have been Davis. But anyways, he must have wondered about how that formed, but we have no clue. And then looking further to the north and also a little to the west, this is the Ardsley Wind Gap, and this is the one at Edge Hill where I mentioned that it had been incorrectly shown. Davis must have known that there was a relatively flat-floored lowland between this sandstone ridge here, which is known as Edge Hill, and a sandstone ridge here, which is known as Camp Hill, and here, and that and he must have been curious when he saw the map, if he didn't know this already, but Sandy Run drains the northeast end of this lowland in a west direction towards Wissahickon Creek, which flows in a south direction over here. But Sandy Run, instead of staying in the lowland and flowing to Wissahickon Creek, which any logical stream would want to do, should want to do. Sandy Run makes a turn to the north, flows through a water gap, cut across this um, sandstone ridge at Camp Hill, and then at Fort Washington, Sandy Run turns in a west direction to join Wissahickon Creek, which is flowing in a south direction through another water gap across the same sandstone ridge. And then Wissahickon Creek flows across the relatively lowland area between the sandstone ridges and enters what is a very deep gorge. It's now the Wissahickon uh, Park area of the Fairmont Park, which is a beautiful park. Uh, and the gorge is about 300 feet deep. This is Chestnut Hill here. Now, Davis must have puzzled why Wissahickon Creek cut this deep gorge here through very resistant rock when it could have just turned in a west direction here and flowed on the floor of this lowland to the Schuylkill River, which is over here. And it could have avoided this gorge here, although that a lot of people in Philadelphia are thankful that Wissahickon Creek did cut the gorge because it's a beautiful park today. Um, well, Davis' uh, solution to the topographic map evidence that he couldn't explain was not to say anything about it. And that was a very common view, and he essentially established the precedent for that. But at the same time that Davis was ignoring the evidence, for all practical purposes, there were other geologists that were being assigned to take the new topographic maps and to use them as base maps for geological mapping purposes. And um, in the southwest Pennsylvania, and this is an area to the south of Pittsburgh, this is the north-oriented Monongahela River flowing north towards Pittsburgh. There were geologists were being assigned to map the geology of the area, primarily to determine where the coal seams were and how much coal was there. But these geologists in their reports were noting other features. And one of the features that they were noting were barbed tributaries. And these are tributaries that are not flowing in the direction of the stream or river that they're joining. And here you can see two south-oriented tributaries flowing to the north-oriented Monongahela River. Another thing that was noted were large abandoned what looked like large abandoned meanders here. And geologists puzzled over these and they noted them in their report, and they speculated on some possible ways that the Monongahela River could have eroded this as a meander and then been somehow been forced to cut a new route, which is using today. But this was never resolved, and there were speculative proposals about how this was possible, but it never, which basically ignored after it was determined there was no way to come up with a good solution. And then another geologist working to the south of that area in another area using the new topographic map for mapping purposes, noted that all the tributary drainage divides, not only did they have long south-oriented tributaries, but they also hugged the southern margin of the drainage divide. Now, I've shown you a small drainage um, uh, basin, tributary drainage basin within the Monongahela drainage system here, and you can see how the main tributary is hugging the southern edge of the drainage basin. Now, this is not the Monongahela River. This is the fork of 10 Mile Creek, and this is the North Fork of 10 Mile Creek. They join here at Clarksville and flow in an east direction to join the north-oriented Monongahela River off to the east here. Now, the geologist who was mapping this area, he concluded that there's just no geological reason why the drainage basins should be asymmetrical. And he said he just couldn't explain it. But his main purpose was not to worry about the drainage system, but was to map the geology in the coal seams. Now, he wasn't the only one, and these geologists up in Pennsylvania weren't the only ones to notice barbed tributaries. Geologists working in West Virginia using new topographic maps noted that the north-oriented Cheat River, which is a major north-oriented Monongahela River tributary in West Virginia, that it had a large number of south-oriented tributaries. I've shown a few of these in a highlighted form here, and that and they said in their report that they were tempted to say that the Cheat River had once had a south orientation, but that they eventually rejected that idea because there were some north-oriented tributaries that they could see, and also that the Monongahela River had already been interpreted by the accepted paradigm as always having flowed in a north direction. And so these geologists, they reported it, and then they went on to deal with the problem that they were looking at, which was to again map the geology and determine where the coal seams were. And there were many other geologists that reported problems with the early topographic map drainage system evidence. I mentioned asymmetric drainage divides and basins. Here's a asymmetric drainage divide between the north-oriented Little Missouri River in South Dakota and North Dakota, and the this is a north-oriented river, and it turns up to the north of this map, joins this Missouri River, which is flowing in a south direction. And look at all these Missouri River tributaries. They begin almost right next to the Little Missouri River. So it's a very much an asymmetric drainage divide that never was explained. It was very obvious on maps, and you didn't even need a detailed topographic map to see it. And there were other problems. I mentioned water gaps at the beginning, and here's the Delaware water gap. This is the Delaware River flowing along the Pennsylvania, New Jersey border here. And the Delaware River is in a valley between Kittatinny Mountain and the Pocono uplands here. And the valley continues in a southwest direction here, but the Delaware River doesn't continue in a southwest direction. It turns in a southeast direction and cuts this deep water gap across Kittatinny Mountain, which is composed of resistant rocks. It's a very well-known site today, and it's a major transportation route. And Davis had trouble explaining it. And as I mentioned, that other geologists also had trouble explaining it. The geology is well known, but why and how and when the water gap was cut is not well known. And as the new topographic maps were being issued, hundreds and then thousands of such water gaps were being found. In Pennsylvania alone, there must be thousands of water gaps if you look closely. And we'll look at some of the explanations for this as I get further in the lecture. Now, in the Rocky Mountains, there was a problem that it was a little different, but here we're looking at Wind River Canyon from the south. This is the Wind River flowing in a north direction, and it's cut a deep canyon that's over 1 kilometer deep through the Owl Creek Mountains, which is a fairly high mountain range. It's not one of the highest mountain ranges in Wyoming, but it stands up more than 1 kilometer high. from the surrounding areas on either side of it. And how this deep canyon across an entire mountain range was cut is something that really puzzled geologists. And like with the Delaware Water Gap, that geologists were really straining to come up with explanations to explain how this could happen. And in this case, one proposal, which is you still find literature today being published about it, is that the Owl Creek Mountains had been buried in sediments up to their top, and that the Wind River had developed on those sediments and then cut down through those sediments into the underlying Owl Creek Mountains. The only problem with that is that there isn't much evidence of the sediments that buried the Owl Creek Mountains. And the same thing, that same type of proposal has been made for the Delaware Water Gap, and there isn't much evidence of the sediments that buried the Kittatinny Mountain. Now, if we look at the Wind River Canyon area, it's in central Wyoming. This is the Wind River Basin in central Wyoming. And Yellowstone Park is up here. The Wind River starts to the south of Yellowstone Park. It flows in a southeast direction here into the Wind River Basin. And then for no reason at all, it turns in a northeast direction and then a north direction to flow through Wind River Canyon. And direction changes like this were just puzzling geologists. They couldn't explain them. And again, many geologists like Davis, they just ignored that because they couldn't explain it. But that that there's just no reason why the Wind River couldn't have just continued in this direction. And I'm going to show you the area just to the east of this. And look at the Sweetwater River here, because this is going to be a reference point. There will be a little bit of a gap between the two maps, but the Sweetwater River does continue east. And so let's look at what's to the east here. And to the east, here's the Sweetwater River, which is a continuation of what you saw on the map before. And here's where the Wind River could have been coming. And as I said, there's nothing blocking it from doing that. And the Sweetwater River is joining the north-oriented North Platte River, which then turns in a northeast direction. It cuts a deep water gap across the northwest end of the Laramie Mountains, and these are the Laramie Mountains that you're seeing here. And this is another mountain range in Wyoming. It's the northern extension of the Colorado Front Range, but it's not quite as spectacular as the Colorado Front Range, but it's a significant mountain range. And it's definitely has the features of a mountain range geologically. It's an uplifted area. But the North Platte River, after it's cut that water gap, it turns in a east direction and then a southeast direction here. And there's no reason why the North Platte River should change its direction here. That it could have continued in a north direction up here to the Yellowstone River. So this is hard to explain. And there's on this map, there are other features here that are just as equally hard to explain. Deer Creek here, it starts out in the Laramie Range. It flows in a south direction. Then it makes a U-turn at the south edge of the Laramie Range and then flows in a north direction in a valley cut completely across the Laramie Range, and it ends up into the North Platte River. Box Elder Creek does the same thing. It starts in a south direction, makes a U-turn, and then flows completely across the Laramie Range. These valleys are not as spectacular as Wind River Canyon, but they are significant valleys cut across a mountain range. And then if we come down here, the North Laramie River, it starts out as a south-oriented drainage system in the Laramie Range. It comes to the edge of the Laramie range, um, and then it turns around and flows in a northeast direction in its own canyon across the Laramie Range. And the Laramie River, it's flowing in a north direction in the Laramie Basin, and then it turns in an east direction to cut its own canyon across the Laramie Range. And there are other features like this that I could talk about, but all of these features are well known. They're on the maps, but geologists can't explain them. And for all practical purposes, they've given up on trying to explain how these things formed because the accepted paradigm doesn't give them the tools that they need to explain it. With that, I want to turn to and look at a few geologists who influence accepted geology paradigm interpretations that are significant in terms of the topographic map evidence. Thomas Schroeder Chamberlain was a contemporary of William Morris Davis, and like Davis, he was a prolific writer, and probably the thing that he's most significant related to this lecture is that he's recognized for his work that helped to originate the concept of multiple episodes of North American continental glaciation. Now, he wasn't the only one involved in this. This was also being recognized in Europe about the same time, and there were other people in North America. He also had many other interests. One of his interests was how the solar system developed, and he developed a hypothesis for the solar system origin that's not too different from some of the ideas that astronomers have today. He did considerable mapping on a part-time basis for the United States Geological Survey. He taught at a number of institutions and was president of the University of Wisconsin for a while, and he later served on the University of Chicago Geology Department faculty, where he probably had the greatest influence related to what I'm talking about. And at the University of Chicago, he developed a number of what are today accepted geology paradigm interpretations, including the concept of glacial interglacial cycles. And he helped the University of Chicago Geology Department become probably one of the leading early 20th century geology research centers, and where they taught many of Chamberlain's ideas to students who then graduated to go out and become professors at other university geology departments, where they taught Chamberlain's ideas to their students. And that's how the paradigm got built up. And the same thing was happening at Harvard, where Davis was teaching his interpretations to his students who went out to become professors at other university geology departments, where they taught Davis's ideas to their students. Now, one of the people that William Morris Davis really influenced, he was not a student of Davis, but he came under Davis's influence, was Douglas Wilson Johnson. Johnson received his doctorate in geology from Columbia University in 1903. He then taught for a short time at MIT and then moved to Harvard in 1907. And at Harvard, he was working alongside with William Morris Davis, who really influenced Johnson during that period. Johnson was so enamored with Davis's ideas that Johnson republished many of Davis's publications, and in his own publications, Johnson frequently promoted concepts that Davis had introduced. Johnson did not stay at Harvard. He moved to Columbia University in 1912, where he continued to teach until 1944, when he died unexpectedly. Now, Johnson, during the First World War, made some contributions related to shoreline processes, and military geology. He also wrote a number of papers about erosional processes that were published in journals. But in 1931, he published this book, Stream Sculpture on the Atlantic Coast, which Johnson intended to be his version of the Davis Rivers and Valleys of Pennsylvania article. And in this book, Johnson is trying to solve the problems that Davis had in his 1889 article, which was largely with the water gaps. And Johnson argued that if there was a marine incursion that buried the Appalachians during the Cretaceous, and that Appalachians were buried with Cretaceous sediments. And remember, I told you about sediments covering the Owl Creek Mountains in Wyoming, and that. And then Johnson wanted the present day rivers and streams to develop their courses on that sedimentary cover. And then, as the sedimentary cover was removed, the rivers and streams just cut down through the underlying structures. And with that solution, Johnson felt he could explain many, if not all, of the water gaps. And it was kind of a neat solution, but as I mentioned, the big problem was the evidence for the Cretaceous sediments just isn't there. Now, Johnson had a student by the name of Arthur Strehler. Arthur Strehler became a graduate student in the late 1930s. He earned his master's degree by studying Grand Canyon area erosion processes. But then Johnson convinced him to do a doctoral thesis related to finding evidence that would validate Johnson's hypothesis for the Appalachian Mountain region drainage system origins. Well, Strehler went out and most of his field work was done in Pennsylvania. He also studied the topographic maps in great detail, and he concluded that there was no evidence for the Cretaceous sediments that Johnson said had covered the whole region. And then he rejected all the other hypotheses that had been proposed up until that time, which included that maybe the water gaps were all located along fault lines. Strehler couldn't find evidence of fault lines where those water gaps are. And then Strehler, in his doctoral dissertation, said that, hey, I can't find any evidence to support Johnson's hypothesis, but I can't find any evidence that to prove that it didn't happen. And then he went on to say that he could pretty much disprove all the other hypotheses. And then later in his life, he determined that trying to solve the drainage system origin questions was a waste of time. So that maybe is what led to Johnson's early death. But in any case, Strehler could not explain Pennsylvania water gaps. This is a Susquehanna River flowing through water gaps to the north of Harrisburg, Pennsylvania, down here. And Strehler, who took over Johnson's faculty position after Johnson's death, Strehler in the early 1950s decided, hey, I can't make this Davisian way of interpreting drainage system and erosional evidence work. So I'm going to change the direction and start using a statistical approach. And I did take courses from Strehler, but Strehler didn't mention this in any of the courses that I took from Strehler. I only learned it when I went to the University of Wyoming after I left Columbia University. But anyways, Strehler developed a statistical approach here where he started putting numbers on streams, and he said that streams with no tributaries, he said, were first order streams. When two first order streams joined, that formed a second order stream, and when two second order streams joined, that formed a third order stream. And so he started to publish about how to use statistics to look at drainage basins. And this may have some value in determining how water flows through a drainage system. In fact, Strehler borrowed this from a hydrologist who had proposed a somewhat similar numbering system a few years before. Um, Now, unknown to me at the time that I took the classes from Strehler, that where he was teaching basically the Davisian uh, model or approach to looking at the topographic map, drainage system, and erosional landform evidence. Um, that Strehler had 20 years previously determined that that approach was a waste of time. Uh, but I didn't learn that until I got to Wyoming. And at Wyoming, I was expected to use this Strehler system, statistical system, in my PhD dissertation to explain drainage system origins. And I couldn't make it work. So I, I, uh, I consider Strehler's system to be as much a waste of time as the Davisian system. And many years later, what I realized was that Strehler and Davis and the many other geologists who were unable to explain the drainage system and erosional landform evidence on the topographic maps, or had unknowingly identified huge volumes of anomalous evidence that the accepted geology and glacial history paradigm cannot explain. Now, I'm going to conclude this lecture with a very brief comment about the Channel Scabland area in eastern Washington. And this map from the Ice Age Floods National Geologic Trail, which is now maintained by the National Park Service, is showing where a large flood which is now recognized to have come from glacial Missoula here, flowed across eastern Washington here. And that today you can go there and you can see the evidence all laid out for the flood. But in the 1920s, J. Harlan Bretz, who was a tenured professor at the University of Chicago at the time, he used field and topographic map evidence to suggest that a huge flood had flowed across this area. And when he suggested this to the geologic community, he did get his papers published because he published them in the Journal of Geology, which was the University of Chicago publication. And so he basically had a journal that would take his papers. But the geology community as a whole rejected his idea. And Bretz, for 40 years, Bretz lived with the idea pretty well rejected. Now, the critics of Bretz, they did have a problem. And their problem was that Bretz was the first one to publish detailed information about the Channel Scablands in eastern Washington. And, um, and in geology, you take basically, you have to look at the literature when you're going into an area. And the critics, they wanted somebody very badly to go out and remap Bretz's flood evidence in a way that would be consistent with the accepted paradigm, because Bretz had violated all the accepted paradigm rules in terms of the flood that he was describing. And so they were looking around for somebody who needed some research money and that would have some credibility when they, in terms of rejecting Bretz's hypothesis. And they found a likely candidate, Richard Foster Flint, who at the time was a newly hired Yale University faculty member needing research money. And he'd also graduated from the University of Chicago, where Bretz was on the faculty, although Flint had not been real close to Bretz at the University of Chicago. And but Flint there was a problem because Flint, when he got to Yale University, he was publishing interpretations of Connecticut glacial geology that differed from interpretations that W.C. Alden had made in Massachusetts, which is just to the north of where Flint was describing the glacial geology. Now, W.C. Alden was a very powerful figure in the United States Geological Survey at the time, and he controlled a lot of the money that was available for research of the type that was involved here. So that they needed Alden's approval. Now, I don't know if there was a plot here, but so I may be speculating a little bit here, but I do know that in 1932, Douglas Johnson got on the train and went from New York City up to New Haven, Connecticut, and spent a weekend visiting with Flint. And Flint, shortly thereafter, published a short paper in which he thanks Douglas Johnson for coming up to visit with him and for showing him the light. And in that paper, Flint completely revises his interpretation of Connecticut glacial geology to conform more closely with Alden's ideas. And that shortly thereafter, maybe a year or so after, Flint starts receiving United grants from the Geological Society of America to go out to the channeled scablands and to remap the area. And Flint did remap the area, and he did so in a way that was quite acceptable to Bretz's critics, which basically was in the context of the accepted paradigm where there was no big flood. And Flint then went on to get funding from a number of different funding agencies and became America's leading glacial geology expert and also a prolific textbook writer. And in the previous slide, I showed you the introductory geology textbook that I used as a when I took my introductory geology course, on which Flint was one of the co-authors. And this book here, The Glacial Geology of the Pleistocene Epoch, was Flint's textbook for glacial geology, which it doesn't mention the eastern Washington state floods that Bretz had described, and it was used by practically every university geology department in the country in their glacial geology courses. And Flint generally was the expert on glacial geology in the United States during his lifetime. Now, Flint died fairly young, and Bretz outlived him. And some after Flint died, Flint never accepted Brett's hypothesis in his lifetime, but after Flint died, that other geologists went out to the channeled scablands and they began to agree with what Bretz was saying. And so today, the channeled scablands, the Bretz interpretation is accepted and the Flint interpretation isn't. But the thing that I want to emphasize here is that Flint, who did not see a big flood in the channeled scabland, pretty much defined glacial geology for the rest of the country. I want to make a few concluding comments before I end the lecture. William Morris Davis, Thomas Crowder Chamberlain, Richard Foster Flint, and the other people that I talked about were all prolific writers and influential geology professors who influenced the development of the geology research community's now commonly accepted geology and glacial history paradigm, which cannot explain almost all of the well-mapped United States Geological Survey detailed topographic map, drainage and erosional system, landform evidence. And I want to conclude by saying that an understanding of the drainage system and erosional landform evidence is important because that evidence is present everywhere on the land surface, and it must have been developed during the Cenozoic era by Cenozoic era geologic events. And you cannot understand Cenozoic geology and glacial history properly unless you understand the ignored and unexplained topographic map and drainage system evidence. And that's why I say there was there's a topographic map mystery, because the geology research community does not know why what that topographic map evidence has to say.